자, 오케이. Okay, this is the chapter 9 of discrete mathematics. We have covered the first 8 chapters, including the graph theory. And now we will start chapter 9.3. And then we will have the presentation of your solutions for the earlier chapters for your final examination. And then on week 16th, we will have a final comprehensive examination from chapter 1 to 9. Chapter 9.3. Yeah, you can find this lecture note on the web and the laboratory for trees in this web address. Okay, yeah, it has 9 sections, including terminology and spanning trees and minimal spanning trees and binary trees and tree traversals and decision trees and isomorphism of trees. A connected graph that contains no simple circuit is called a tree. And in 1857, Arthur Cayley used this concept of trees to count certain types of chemical compound. Since then, it has been used to solve problems in a wide variety of disciplines, particularly in computer science. For example, these trees can be used in algorithms such as Huffman codings, and we can develop algorithms to construct network containing the least expensive set of telephone lines linking different network nodes. Okay, trees looks like these. Okay, like this. And a place that has a lot of trees like this can be called a forest. You have seen this type of graphs for the NCAA tournament and other sports event. This type of tree is called the tournament trees. Okay, like Elite 8, Final 4, Semi-Final, and Final. Like this, yeah. So you have seen many of trees before, and this is also example of trees, and also family trees, like this, is also an example of trees that we're gonna study. This is my mathematical genealogy. This is my family tree in mathematics. My academic fathers and grandfathers and great-grandfathers include David Hilbert, Felix Klein, Lefschutz, and Poisson, and Lagrange, Leibniz, etc., and Marcus, Frobenius, and those are Karl Weierstrass, and those are and Gauss also. So this is a kind of genealogy tree, family trees. And also I have my academic sons like this. So this kind of concept can be drawn in a graph with family trees like this. And this is also one example of trees. Okay, so we start with the official definition of tree. A tree is a connected, undirected graph with no simple cycles, okay, like what you see. And a forest is a simple, undirected graph with no simple circuits. If you have a bunch of trees, then it can be called a forest. And root tree is a tree that has one vertex which has been designated as a root. So it starts from the father and sons and grandchildren's and grandchildren's like this. So it starts from one root, then we call it has it is a it is a rooted trees. So this is all those processes start from here. So it has a root, but this one doesn't have a root, and this one doesn't have a root. So these are not rooted trees. Okay, and in a rooted tree, a unique simple path from a vertex to another vertex does exist. Okay, unique simple path. If we have a rooted tree, then we have a unique path from one vertex to another. For example, from V2 to V7, then we should go here from V2 to V1 and V1 to V3, then V3 to V7. So there's only one way, one path to go from here to here. Okay. In graph theory, rooted trees are typically drawn with their roots at the top, like this. Okay? Root at the top, this way. And level of vertex. The level of vertex is the length of the simple path from the root to V. Okay, level. And height of a rooted tree is the maximum of all level number of its vertices. For example, in this graph, in this rooted graph, this is the level of vertex. The level of vertex is 0, and these are level of vertex of these vertices are 1, and here level of vertices are 2. 1, level 2, level 3, level 4, like this. Okay. Top root has a level 0. Only root has a level 0, and all others. Okay. So it has a root here. And a rooted tree is often used to specify hierarchical relationships like this. In the university, the administration organization chart shows hierarchical relationships like president and vice presidents and deans and chairman of the department, etc. Like this. This is a hierarchical graph. So it's an example of a tree also. And also in your PC, you have the directory structures. Like here on the desktop, you have my document and my computer and my network places. And in my document, you have my pictures, my musics, and faxes. And in my computer, you have C directory, D directory, and then so this also this structure in your PC also has a tree structures. PC. Hierarchical definition trees. So in database, like hierarchical definition tree. If you have a book, then book has author, location, and publisher, and availability. And so in your library, then when you organize the books, and you should have these hierarchical trees. So the student can find the book exactly if you follow the right path. Okay. So, Okay. Huffman code is a lossless data compression algorithm. Okay. There is a detailed explanation in the Wikipedia, and also there are many good lectures on Huffman's algorithms that you can easily find. There are enough informations. Okay, I will show the example of Huffman code. Here, this is an example of the Huffman code for the rooted tree, and the next algorithm is the way to constructing an optimal Huffman code. The problem of Huffman code is this. Given a set of symbols and their weight, okay, a set of symbols and their weight, then find a prefix-free binary code with the minimum expected code word length, which means a tree with minimum weighted path length from the root. This is the definition of Huffman code problem. Okay. Here is the examples. The following algorithm begins by repeatedly replacing the smallest two frequencies with the sum until a two-element sequence. For example, if we have these 5 numbers like this, then smallest two number 2 and 3 are added. So you have 5, 7, 8, 12. Then you add this following, the smallest 2, which makes 12, which makes 12. So 8, 12, 12 is the number that you have. Then add the smallest 2, so which gives you 20. So 12 and 20. This process can be drawn in these trees. Okay. So 12, 20. This 20 is divided, can be split as 8 and 12, and this and 12 also split it as 5 and 7, and 5 split it as 2 and 3, like this. Okay, this is this figure shows how the Huffman code algorithm works. Okay, here is the explanation on Huffman's code.
Welcome back. We're talking about symbol codes, and in the previous video we wrote down these 3 desirable properties of a symbol code. We said we'd like it to be efficient in terms of getting good compression. Well, we'd also like it to be fast so that we can encode and decode very quickly, and we'd also like it to be simple so that we can understand it very easily and also implement it easily.
Huffman code.
And to start getting a handle on B and C, to understand what properties of a symbol code might give us good speed and simplicity is a
This shows how that algorithm works, but I will explain
to the node for the other code.
Quicker way.
Nice way to think about them.
So,
and one other thing I'd like to mention here.
You can find the details from there, but let's see how that algorithm works. This algorithm constructs a tree working backward, beginning with the 2-element sequences, 220 in figure 1.13, as you saw. 220. As you saw. For example, the second tree is obtained from the first by replacing the vertex level 20 by the tree in figure 1.14 as 20 the sum of the 8 and 12, and finally to obtain the optimal Hoffman coding tree. So we replace each frequencies by a character having that frequencies, like what you see here. And these trees are used in many other the disciplines, including the chemistry. And these are the isomer of butan, that also, which has also three structures. I will give more explanation later. We now start with the terminology of trees and characterization of trees, parent and child, etc. Here. The internal vertex is a vertex that has at least one child, internal trees. So this one has a child, this one has a child. So these are the internal vertices. Terminal vertex is a vertex that has no children. So the very end ones, which do not have the child, are called the terminal vertices. And the others above it are called can be called the inner vertices. The tree in example has internal vertices and 4 terminal vertices. And this part is called a subtree of this whole tree, rooted at this vertex, like this. If we have a tree like this, rooted tree like this, then this part can be considered as a subtree rooted at this vertex X. So for example, this is also a subtree of the whole rooted at this vertex. Okay? Subtrees. So family trees can be a good example of those. In the Greek history, and like this, Uranus has 4 children, and Aphrodite has 1 child, and Zeus has 4 children, like this. In here, for example, then Kronos has his children, 4 children, and 4 grandchildren. Then this piece of the graph is called the subtree of whole these family trees, like this. Okay, like this. This is a subtree rooted at Kronos. Okay. subtree. So 그러니까 여러분들도 이제 나중에 이렇게 결혼해서 분가하면 여러분으로부터 이렇게 여러분들의 가족 트리가 또 따로 만들어지는 것이죠. 이렇게 분가할 때 족보도 지금 이렇게 만들어지고 이제 호적도 결국 이런 식으로 윤리되는 거죠. Okay, so yeah, you may have your own family trees as a subtree. Okay, so formal definition of subtree. Subtree over T is a tree T prime such that vertex of T prime is a subset of vertex of T, and edges of T prime is a subset of edges set of T. So, for example, this is a whole trees, then this is a whole tree, then this part is a subtrees. This can be a subtrees. So this part can be a subtree of, and this part also subtree can be a subtree of whole. Here rooted at C, here rooted at B. Tree. but tree cannot have a cycle in it. So if this is a simple cycle, if we have a graph which has a cycle like this, then it cannot be a tree. A graph with no cycle is called an acyclic graph. Acyclic. Acyclic means there's no cycle. And the following four statements are equivalent. The TBR graph with n vertices, then the following are equivalent. T is tree and T is connected and having no cycles, if and only if they are equivalent. If T is connected and has n-1 edges, n-1 edges, if you have n vertices and n-1 edges, then which means is only connected up to this and there's one missing. So it should be trees. And it is acyclic and has n-1 edges. So yeah, they are all equivalent. You can easily check it. I left the summary of the terminology for the rooted tree in this page. Suppose we have a tree like this, then we call this a parent and this a child, and in the level of a child level, we call it siblings, like 형제. It's called two vertices with the same parent are called siblings. Okay. And a leaf is a vertex with no children. The one 말하자면 총각 또는 처녀라는 의미죠. 아직 결혼하지 않은 그런 거. Leaves 제일 끝에 꽃 잎 같이. The terminal leaves is a vertex with no children. So these are called the terminal vertices. Known leaves are called internal vertices. Which is not a terminal vertex, and they are internal vertices. So these are internal vertices, R and V, and these are internal vertices. And A, C, D, E are terminal vertices, which is also can be called as a leaf. Height of the root tree is the length of the longest directed path. Here in this case, level 0, level 1 and level 2. So we have 1, 2, 3. Height of this tree is 3. Okay, isn't it? Height of root is the length of the longest direct. In this case, this is 1 and 2. So this is 1. The height of this rooted graph is 2, because the longest distance of the path in this tree graph is 2. So height of this rooted graph is 2. And ancestor, the R is called the ancestor of V, and B is called the descendant of R. 그러니까 B의 조상이 R이고 R의 후손이 B고, 또 C도 R의 후손이고 descendant고, 또 R은 뭐 C나 D나 E나 B나의 ancestor가 되는 거고요. Subtree, yeah, we have defined it. Next, a rooted tree is called the M-nary tree. If every internal node has at most m children, like Mr. Ham said. It is called a full M-nary tree if every internal node has exactly m children. An M-nary tree with m is equal to is called a binary tree. At most m children. So in this case, each vertex has at most 2 children. Here it has 1 children. It has 2 children. This one has 2 children. This one has 2 children, and so this is the example of trees. And this is a binary tree. In this case, this one has 3 children. This vertex has 3 children, and this vertex 3 children. and or no children. So this is called, this is an example of ternary tree, which has at most 3 children. This case 5. So this is 5 fifths, finally. And so these are examples of M-nary trees. Next, section 9.3, spanning trees. Finding a subgraph T over graph G such that T is a tree containing all of the vertices of G, and this tree is called a spanning tree. So, T is called the spanning tree of a graph G if T is a subgraph of G that contains all of the vertices of G. So spanning tree는 그 뭐냐면 서브그래프인데 모든 버텍스를 포함하는 서브그래프. 연결된. For example, in G, if G is a graph, then we can find the subgraph that connect all vertices like this. Then this blue colored one is called the spanning tree. So we can have more than one spanning trees. A spanning tree of the graph G of figure 33.1 is shown in black. So in this graph, the black edges is here, 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 here. So this includes all the vertices which is connected. So this is called the spanning tree. 그러니까 spanning tree라는 소리는 생성한다는 그런 의미니까 if we have this black graph, black subgraph of G, then we can get the original graph by just adding some edges on it, isn't it? Similar to here. Okay, so we can have many spanning trees. So in a graph, we can have several spanning trees. We can have, as we see. A graph G has a spanning tree, and that are A and B vertices of G. Then, with this argument, then we can show it is connected. So suppose if this graph has the spanning tree, this graph has a spanning tree. So as you see, it is all connected. You can reach any of the vertices from any of the vertices. It's all connected. You can start. You can start from a vertex, so you can reach it to any other vertices if it has a spanning tree. So having a spanning tree is an important property. The following theorem shows that if G has a spanning tree, if and only if G is connected. So if it's connected, then it has a spanning tree. If it has a spanning tree, then it is connected. Okay. This is a very important property of a connected graph. Okay. Yeah, this is the graph that you see. And I have made a code on trees. This in this laboratory, I have introduced the earlier lectures. And here trees, definitions, and here this code, the Sage code based on Python, gives us whether the given graph is a tree or not. So these vertices, these edges, draw the graph, and it shows it is a tree, and it is connected, and it has a spanning trees. If suppose we have 4 like this, then it still is a spanning trees. But if we have, if we delete this, what happens? Then, as you see, the graph of this is looks like this. So it's not connected. Okay, so it's not tree. Okay, and so this is a command to draw the graph and to check whether the given graph is tree or not. And next, the level, and I made another code here and show Huffman code. Yeah, this code shows to find the Huffman code for a given graph, like you see. So for a given string, you can find the optimal Huffman code for this string with this tree. So given code gives you a code. This Huffman code can be used like this, and subtrees, and ancestors, and descent, and spanning tree, and here also multiple edge. We can draw the graph of the here. This shows this go. From here we can find the spanning trees of this given graph, and we can find the minimal spanning tree from this given tree. Like with this simple command, this gives you these 169 spanning trees exist. There are 169 different spanning trees, and this is the minimal spanning tree that we find, the shortest one. Okay, and this command gives you those. This code gives you the answer that you are looking for, and there are more. Yeah. I asked you to try to find, try to make a code from the given pseudo code that works on this. These are typical hallmarks of it. Anyway, so for the spanning trees and minimal spanning trees, and whether the checking the tree, whether the given graph is tree or not, can be easily checked with the code that I introduced. And next, breadth first search. This is called the 너비 우선. breadth 폭이죠. 너비 우선 탐색. This explanation can be found in here. breadth search. So 그러니까 이게 이제 너비 우선이니까 서치를 할 때 이렇게 이런 식으로 위에 루트에서 시작해서 이제 평행 쪽을 먼저 하고 그 다음 아래층 레벨에서 또 평행 너비 평행을 먼저 하고 그 다음 레벨에서 또 이런 식으로 해서 차근차근히 모든 버텍스를 거쳐가는 방법을 너비 우선 breadth first search. It is called the breadth first search, like this. It follows each levels from the root, from the top. Okay, this is called the breadth first search. And in here, we do start from the rooted, and then like what you saw. It finish up the first level, and then second level, and third level, etc. And from that, this breadth first search algorithm can be used for finding a spanning tree. And that's what you have seen. These are the pseudocode for that algorithm, and that algorithm is shown like what you see in this figure. Start from here. Input is a connected graph G with the vertices ordered like this. Then output is a spanning tree T. And the algorithm is start from there and then go through the first level and then second and third like this. Check. Okay, this is one algorithm. Breadth first search. And the other one, an alternative to breadth first search is the depth first search, 깊이 우선 탐색, DFS, which proceeds to successive level in a tree at the earliest possible opportunity. Depth first search. Idea of depth first search is to proceed to successive levels in a tree at the earliest possible opportunities. This is algorithm for finding spanning tree with depth first search. The graph looks like this. This input for the depth first search is the input is a connected graph G with vertices ordered, and then the output is a spanning tree. Algorithm is like this. Algorithm is like this. Start from depth. Before it was the breadth, but in here, in depth first search, you go D first, and then next to right, and then. So go D first. So that's why it is called the depth first search. So depth first search can be seen in this way. And the concept of backtracking are used in here. This algorithm can be used for 4 queens problems. You must have seen these 4 queens problems. 4 queens problem like this, or n queens problem. Arrange these queens, and so she cannot see other queens on vertical and horizontal. So this is a way that you arrange 4 queens in 4x4 chessboard. This idea can be expanded. So this algorithm, so we need an algorithm to locate the first queen and the second queen and third queen and then fourth queen like this. This algorithm can be expanded for n by n chessboard. Okay. This explanation can be found in many.
Hello guys, today we're learning what exactly is the n queens problem and how do you solve it. We'll be solving it logically here. And so n queens problem is basically you're given n number of queens and you have to place them on a chessboard of the given size. Right now we're taking say n to be 4 and the chessboard is 4. No more than 4 queens can be placed on a chess queen problem of the given chess, as this one is not yet in the attacking position. I mean in the attacking path. The third queen can go here, and you cancel out all these positions as well, and the fourth queen can go in this position. So now you can see that no queen is attacking any other queen, and they're placed safely. This was the 4x4 n queen problem. Let us see the 8x8 n queen problem.
By n.
In this, we place the first queen in the 4th row here, and we will cancel out the rest. The second queen is placed out here. We will just cancel out the rest. Cancel out the full row, full column, and whatever is diagonally possible. We will have to take care only going through the white squares. Alright. The next one is the third queen. We are putting in the third checkbox, and cancel all the rows and columns and diagonal.
the whole n queens
Okay, wait, this is wrong.
on the right place.
Anyways, this is already cancelled, so anyways, 8 by 8. And similarly, if you have a n queens board size 16 by 16 problem, you can't place more than 16 queens, but then that is way too complicated. You can program and set the board size, and accordingly you can give the number of queens, and the computer will give you a solution. Okay guys, thank you.
Hello friend.
You can find the good explanation on each of these concepts, which is very popular already. And next, solving the 4 queens problem using backtracking. Also, backtracking concept was introduced.
Hello friends. Today we are going to discuss the n queens problem using backtracking. So, in this problem, we have to put all the n queens in a n cross n board in such a way column
backtracking. Backtracking idea can be here. Okay. Many constructions has been given to generate solutions to n queens problem. For all n's bigger than 4. Okay, here.
Okay, who had the veggie ramen? Who had the veggie ramen?
That's me.
Who had the veggie ramen?
Hello friends, my name is Tushar and today I'm going to talk about n queen problem. So you're given an n cross n board and there are n queens. You have to find any placement of these queens on the board so that they do not attack each other. For example, we have 4 cross 4 board and
backtracking
any square
concept is introduced.
So what this guy is going to do, or the first level of regression, is 1 and 1 plus 0 is 0.
Is 0 comma 0, and then we put this into position array, so 0 comma 0, and go to find another the squares on the third one. So ultimately we're not just one solution. I also have this code here, solve.
Okay. So there are many solutions were already found for 4 by 4 chessboard, the 4 queens problem here, and what the analysis was given like this: do start from here, then first, second, third, fourth, and fifth, sixth, seventh, eighth, like this. As you see, the way that you go through is just like you are using the tree for finding the solutions. The tree generated by the backtracking algorithm in the search for the solution to the 4 queens problem. That's why the concept of root and the algorithm related with the root are important on the real life problems. Okay. And next, minimal spanning trees. Given a weighted graph G, a minimal spanning tree is a spanning tree of G, the sum of whose weight is minimum. Okay, so we have learned the spanning trees, and we are talking about the minimal spanning tree that we could find via simple code. But here, 6 cities from 1 to 6, and cost of building load between certain pair of them. Okay, what will be the cost-effective load to build up between these 6 cities? So, for example, on this graph, if this is weighted like a distance, then this is one spanning tree and this is another spanning tree. But for this connect all the 6 cities in the 1, 2, 4, 5 cities. It has, but the cost is 8. But this tree also is connected. It connected the graph in tree, but also this spanning tree of this, but the cost is only 7. So when you build up the highways connecting these cities, then this would be more cost effective. So the minimal spanning tree. So this is the cost is less than the cost of this. So these ideas can be studied as the minimal spanning tree. So for a given weighted graph, a minimal spanning tree of G is a spanning tree of G with minimum weight. The weight of this graph is 8, weight of this graph is 7. Okay, same ideas. Okay. The algorithm to find the minimal spanning tree that we will discuss is known as a Prim's algorithm. Here's a Prim's algorithm. Prim's algorithm for a minimal spanning tree. The input is a connected, edge-weighted, undirected graph. Okay, we have a weighted graph, undirected, connect. The minimum, so the output would be a minimum cost spanning tree T for G, and this is the algorithm. Okay, and the algorithm can be written in this way in detail, and also it can be learned from the given lecture.
I can't say squat. 이 문장의 뜻은 외워, 적어, 읽어, 들어, 주어. 나는 동사 할 수 없다, 보다. 목적어 squat, squat.
Prim's algorithm for computing the minimum spanning tree of a graph. Now let's start off with some basic definitions. What is a spanning tree? A spanning tree is a subgraph that has the same vertex set as the original graph and is also a tree, which means that it must be connected and must not contain any cycles. A graph may have large number of spanning trees, but not all of them are minimum. A minimum spanning tree is a one in which the sum of weight of edges is minimum. For example, consider the given graph shown here. The edges highlighted in yellow are the edges of the spanning tree. Now both the trees shown here form one spanning tree because each of these contain 4 vertices.
Okay, so yeah, you can see the algorithm, how the Prim's algorithms are working.
Me is parent as you. Finally, this print MS
in here. And I already gave you a finding the algorithm to find the minimal spanning trees. Anyway, here is the this example shows Prim's algorithm, how the Prim's algorithm work for finding a minimal spanning tree for the graph. This here, if you follow those explanation, then you will easily understand Prim's algorithm like you saw from the given lecture. Anyway, a minimal spanning tree will be constructed when either edge is selected. So first, the edge 1, 5 is selected, then the next find then with that algorithm, then find the next edges with the minimum weight, and then find the next vertex, next edge to be selected, and this at the end the minimal spanning tree constructed in the which is shown in the figure 4.3, and that it shows how that algorithm works. So in that figure, the shortest path from A to G is ABG. And the important thing is this Prim's algorithm furnishes an example of a greedy algorithm, which means an algorithm that optimizes the choice at each iteration. You have to do it all the steps in principle can be summarized as doing the best locally. In Prim's algorithm, since we want a minimal spanning tree at each iteration, so we have to do lots of computations. Prim's algorithm is correct. At the termination of algorithm is a minimal spanning tree. Yeah. So that algorithm, with that algorithm, yeah, our output will be a minimal spanning tree from the given one. And I have shown you those some of the examples of code, and I asked you to find a couple, to make an algorithm from the given pseudo code that works. Even though you can find the code which was already made. So depth first search and Fouquet's problems and Prince algorithms are good examples to practice. Next, binary trees. Let's have some 5 minutes break before we continue the binary trees. Any questions?